everybody. So in this video, we're going to discuss one example on the flow rate calculations using orifice meter, which is one of the three flow meters that we discussed in the previous video. So in this example, we have methanol that is flowing, and we know the density and the viscosity of this methanol. It flows through a 4 centimeter diameter pipe. So this is the pipe diameter. And we have an orifice of diameter of 3 centimeter, and there is a mercury manometer that's used to measure the pressure drop across the orifice. The differential height is 11 centimeter of this manometer, and based on this information we need to calculate the volumetric flow rate of methanol through this pipe. Okay, I just put here the information that we know, and from the manometer we can find the pressure drop in or the difference in pressure between points 1 and point 2. We know that these 2 points are at the same height in the same connected fluid, so the pressure here is equal to the pressure here. And so we can say that the pressure at point 1 is P1 plus rho methanol times G times all this height. I call this length or this height L, so it's L plus 0.11 or the delta H of the manometer. On the other side we have the pressure here is P2 plus rho methanol times G times the same height L plus rho mercury G delta H manometer. This is the same as this, so they will cancel out, and from this we can find delta L, which is rho mercury minus rho methanol times G times delta H manometer, and by substitution we can find the pressure drop to be 13,825 Pascal. Okay, so this is fluid statics, so it has nothing to do with the flow meter calculations itself. But from this we were able to find P1 minus P2, which is an important piece of information. Now let's go to the orifice calculations. One of the very important parameters is beta, which is this diameter over this diameter, so it's 3/4, which is 0.75. And we can apply the equation of the volumetric flow rate for the orifice. So it's CD times A naught times square root of 2 delta P over rho 1 minus beta power 4. We know everything here. Of course, A naught is the area of the orifice. So I substituted with pi over 4 the orifice power 2. And of course, the density here is the density of methanol. It has nothing to do with the manometer, as the mercury is not contributing anymore. So the equation will be V dot equals this number times CD. Now, of course, we don't know CD because CD is, if you remember from our previous discussions, that CD was a function of the of Reynolds number for orifice meter. It's constant multiplied by or function of beta. We know beta, so it's not a big deal, and it's function also of Reynolds number. So we don't know Reynolds number, so we need to find Reynolds number now. So Reynolds number is rho UD over mu. Of course, this rho is the methanol density. U and D are the velocity and the diameter at this this point. Okay, because this is the Reynolds number of the flow. It's not specifically for the orifice. And we put the velocity as the volumetric flow rate divided by area, because we don't know the velocity. And by simplification, this square will cancel out. 4 will go in the numerator, and then by substitution we will find that Reynolds is constant times V dot. And by substituting in the formula of CD, we can find out that we know everything except Reynolds, but we put Reynolds as a function of the volumetric flow rate. So at the end, the equation would be CD is a function of the volumetric flow rate. So the equations are now ready. So we have two equations now: an equation that has CD as a function of or V dot as a function of CD, and CD as a function of V dot. So there are two equations and two unknowns. In the textbook, the solution was by trial and error. So they assumed the value of CD and then calculated V dot, substituted here to recalculate CD, and then keep doing this many times until the the value is constant or is not changing. This is possible, and also it's possible to combine both equations. So we can substitute with v dot in here, and now we have one equation and one unknown. It's not going to be solved directly. It has to be solved by solver or by trial and error, but it's going to be only one equation, which should be less time consuming. And by solving the equation, we find the CD to be 0.60015. V dot is almost 3 times 10 power minus 3 meter cube per second, which is almost 3 liters per second. And we can calculate the velocity, which is the volumetric flow rate over area, which is this volumetric flow rate over this area. We know the volumetric flow rate, and the area is pi over 4 the uppercase D power 2, which is 2.42 meters per second. In the textbook, the result that we got for the volumetric flow rate and the velocity are the same, but CD is given in the textbook to be 0.601. And I think this is a typo in the textbook, because I have exactly the same values for the volumetric flow rate and the velocity. So I double checked, and it's the number that I get all the time. So anyway, so these are the outputs that we got. We have one more case to discuss, inshallah, next time, which is going to be about using pitot tube to calculate the volumetric flow rate. So this is what we are going to discuss next time, inshallah. See you.